Hey guys, it's Mr. Sheeline here. This is going to be the Unit 7.3 notes covering enthalpy and reactions. So here we're now going to start really getting into thermochem in a strange kind of baby step kind of way. So here we're going to be looking at the change in the heat, the change in the energy within particular reactions, chemical reactions. And this will help us determine if a reaction is endothermic or if it is exothermic, and this should provide a bit more, in a way, a bit more clarity as to which one's which. Okay, so what is thermochem? This is what we have been working towards. This is the study of changes in heat within chemical reactions. Okay, and we're getting now really into the kind of the meat of it with enthalpy, and then we'll really get into it when we get to calorimetry. So enthalpy is simply just the change in the heat for a reaction, and we designate this with the symbol of delta H. Okay, so this delta right here, that triangle, and then H. Now what does that delta mean? Well, delta, that little triangle, just means the change of. So delta means the change of. Okay, now I want to say that you should have seen this before, but that's what delta means. The triangle just means a change. And it's going to be a change of what? The H is just going to be heat. Okay, it's a change of heat. Okay, so when pressure remains constant, and this is a pretty important piece right here, and for the most part, all problems we're working with will have pressure remaining at constant. The heat absorbed or released during a chemical reaction is equal to the enthalpy change for the reaction. Okay, so that's heat gained or heat loss. Okay. How much heat did we lose during an exothermic reaction? How much heat did we gain during an endothermic reaction? Okay, and we can denote it like this. We can just say, well, the change in our enthalpy, the change in the heat, is going to be the amount of energy seen in the products minus the amount of heat in the reactants. We don't really, at least when we're practicing like in this particular amount of notes, we really don't use this. It's just to show you that this is how we compare it. It's products versus or minus reactants. Okay. Now, if we have an endothermic, this is where, again, the reaction absorbs energy. Our product should have more energy than the reactant started with. So we would have a positive delta H. Okay. This would indicate an endothermic reaction. But if we have it where the products have less energy than the reactants, then we would have in this case, we would show a negative enthalpy, negative delta H, which would indicate an exothermic reaction. Now again, we've already mentioned that this is when pressure remains constant, so we're going to keep things for the most part as constant as possible. So that means we're going to use the standard state of most substances. So this is what's known as like a pure form of a substance. So water at room temperature under normal conditions is going to be a liquid. And we're going to assume that water in all these reactions will stay roughly speaking, around the temperature where it stays a liquid, and also at a pressure that keeps it at a liquid. We're not, okay? So, and this is important because, I mean, think about it. If we have instead a gaseous form of water, that means we have there's a higher, or sorry, if we are, I guess if we want, think of it this way, if you wanted to use water vapor for whatever reason in a particular calculation, but you're starting with water, you have to input in a particular amount of energy that's needed in order to change your water to a vapor, right? And that takes a substantial amount more of energy, because we saw that in our heating curve diagrams. But anyway, so I'm blabbering on just to say that we're going to keep things simple, and we're going to keep it at the standard state of the substance. Okay, again, so it's like water, we're always think of it as a liquid. Hydrogen is going to always be like hydrogen gas. Oxygen is always oxygen gas, etc., 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 right? And then so we have then because we're keeping things at a standard state, we also have standard enthalpy change. So this is what we're going to be calculating. It's the change measured when both reactants and products of the reaction exist in their standard state. So again, it's just to say here, this little spot is to say that it's a condition we're keeping to keep things simple, to keep things super duper straightforward. Okay, because things get complicated when you're when you're doing phase changes, things get complicated if you don't take into account the fact that the water you're using is actually in gas form rather than liquid form, or that your water that you're using or measuring is in solid form rather than in liquid form. Okay? Like, it makes a big difference, because that's going to change how much energy has to go into the system, how much energy is lost, how much energy is gained. Okay, it's like a completely different game here. So again, we're keeping it simple. So, okay, now we can depict enthalpy, which again is just a change in heat. We can depict these with diagrams, and fairly simple, straightforward diagrams. So all these diagrams are going to be is just a visual description and depiction of the relative enthalpy of the reactants and products in a reaction. So, and we have them both here for exothermic reaction, endothermic reaction. They're super duper similar. They're pretty much the same, but there are some differences between them, and they're fairly obvious. So just real quick, notice that here is our complete and balanced chemical equation. And notice real quick before we move to showing the diagrams, there are these little G's here in this one, and then there's a G and an S in this one. You can just make a note that G just stands for gas, the S stands for solid, okay? And then L, if you didn't guess this already, L is just, it stands for liquid. So this is part of the whole standard state of the substance. Chemists, what they'll do is they'll write out just like this, in parentheses, what the form, the state of matter the particular chemical is in. We're going to ignore it. It's just there to add a bit more, I guess, depth and context, and to familiarize yourself with, a bit more detailed chemical equations. Okay, for right now. So again, so we have all these guys. That's a gas. Oxygen's a gas. CO2's a gas. Water here is, in this case, it's a gas in the product side. Carbon is a solid. Water is a gas, etc., etc., etc. Okay. And then after the complete chemical equations and balanced chemical equations, we have our change in enthalpy. So what this is saying is that it's saying that once you carry out, you have the proportional amounts of reactants, and then you measure out the proportional amount of products. Here is the change in the heat from here to here. So it looks like in this reaction, it looks like in this case, I know that this is combustion, so it looks like we lost energy in here. Not only does it, I know that just kind of looking at it, I know that because I have a negative enthalpy. Okay, so again, remember, negative enthalpy is going to determine and tell you that's an exothermic reaction. While this guy over here has a positive enthalpy, so it has positive 113 kilojoules. And so this tells me this is an endothermic reaction. Okay, now how do we write this? Well, we write it out almost like it's a graph. So we have a y-axis and we have an x-axis, okay? And what we're just depicting is we're depicting specifically what's happening over time, the change in energy over time. So time is going to go on our x-axis here, while energy is going to go on our y-axis here. Okay, write all these in. So we have energy, and energy, you could swap out energy for enthalpy, honestly, you really could. Okay, energy or enthalpy, either works. I typically write energy, but if you want to write enthalpy, that works just as well. So what we're doing though is we're just showing like that we're going from a lower state to a higher state of energy if we gained energy, or a higher state to a lower state if we lost energy. So here in an exothermic reaction, we know that we lost energy. So the way we show this is that we draw a little line here, then an arrow pointing down because we're losing energy. We're lowering the energy level of this particular substance as we go from the reactants to the products. And that's what we put on these little lines. So over here, we put the reactants. And then over here, we put the products. So I'm going to write out the products as I see them in my complete balanced chemical equation. And then I'm going to write out my products as I see them in the same chemical equation. All right. And again, and so now I've got to depict the amount of kilojoules either lost or gained by doing this. I'm going to put my delta H, okay, little degree symbol, and then negative 2043 kilojoules right here. And I'm putting it like right here by the arrow to show like, well, here's how much energy was lost. When we go from here to here, when we have combustion of, I think that's butane, in oxygen, we're going to lose this amount of energy, and our products CO2 and H2O are going to be produced. And so that would be it right there. That is what we would have for our diagram. For endothermic reaction, it's just kind of the opposite. Instead of going from a higher to a lower energy state, we're going from a lower to a higher energy state. Okay. And so we just basically flip-flop it. We're going from lower to higher because we're gaining energy, so we're going to still write our product or our reactants over here. So carbon plus O2 or H2O, goodness, H2O. And then our products, carbon monoxide and then hydrogen gas. We're going to show our change in enthalpy, which in this case is a positive 113. Now, you don't have to draw these positive symbols. It's fine if you keep them out. That's not going to be part of the grade for any of this. Okay, and then here we would show that we're going from a higher energy or lower energy level to a higher energy level in the form of an endothermic reaction. Okay, now this is how I'm going to grade them. So, because you will be asked to practice these, and this is how I grade them. So these little diagrams are going to be out of 4 points. Okay, the idea is that 1 point is going to be for the axes. So it's 1 point for showing me energy on the y-axis and time on the energy on the y-axis, time on the x-axis. There's a point for the orientation of basically of, how did I rate this the other day? Orientation of reactants and products. Okay, so meaning like I'm showing properly that I'm going from a lower energy level to a higher energy level in an endothermic reaction. And over here, I'm properly showing an exothermic reaction by going from a higher energy state to a lower energy state. So if you were to flip-flop them, let's say it's an exothermic reaction and it looks like this, but everything else is fine, you just lose 1 point. You know, if you had your product or your reactants right here, you still had your products over here, you had the enthalpy change right here, you know, all that's good, but you just forgot that you're going from a higher to a lower and not a lower to a higher, it'd just be a -1. Okay, it's +1 for including products and reactants. So we wrote them out like CO, so our products of carbon monoxide and hydrogen gas, and then our reactants of carbon and water, like that. That's all good. That's 1 point right there. And then it's going to be +1 for providing the correct delta H. And we'll get to where we have different delta H's than what's been provided in the examples on the next slide. So as long as you have the correct delta H, you've included the products and reactants, you've got the correct orientation, and you've labeled your axes properly, these bad boys are 4 points apiece. Okay, let's keep on trucking. All right, so creating an enthalpy diagram right here. So you can create this on your own right now, and I'll just kind of walk with you while you do this. So here we've got CH4, and it's going to combust with O2, and it's going to yield us CO2 and H2O. And during this enthalpy change, we are going to have negative 890 kilojoules change here. So meaning we're going to have a loss of energy, okay? We're going to have a loss of energy here, so. All right, so this tells me that we're going to have an exothermic reaction because we're losing energy. And we're going to show it like so. We're going to have that, and then that, and then that. And we're going to have this. Okay. And then we're going to put this here. And we're going to put our products over here. Okay. And so then we have our proper diagram here, and again, that'd be 4 points. So here, I'm going to, let's see, I'm going to actually cut the video right here, guys, and then I'm going to have a second video that I'll pick back up on to walk through the examples, how we can calculate some changes. So if you have any questions for me, make sure you get back to me. If not, I'll see you the next one.